A very good morning to all of you. In this session, we will discuss about resolution. So, resolution, there are many steps are there. First step we have already seen in the last session. That is, we have a set of facts and we can convert it into WF. And next step is converting this WFF into closed form that we will discuss in this session. First, we will see what is resolution. So, resolution is a single powerful inference rule that a computer can automatically prove whether a statement is true or false. So, this we can connect to the real uses like a AI reasoning system, automated theorem provers. So, here we can consider an example. We have a sentence: if it rains, the ground is wet. So, our sentence is: if it rains, ground is wet. So the ground is not wet. Can it be raining? The answer is no, right? So here the resolution works by assuming the goal is false. So here we are assuming that the goal is false. And if that assumption leads to a contradiction, then the goal must be true. So here the resolution means we have a knowledge base and a negated goal. So we are starting with the negated goal and knowledge base. And it leads to a contradiction or empty clause. We will discuss in detail what is this empty clause and all. If there is a contradiction or empty clause, that means that our assumption is false. So what is our assumption? Our assumption is negated goal. That is false. So false means inconsistency. Therefore, the goal is true. Our assumption is negated goal, and we are starting with the knowledge base and negated goal. And if it leads to a contradiction or empty clause, that means that our assumption is wrong. That means our goal is true. So the resolution, there is a first we have a set of facts and we have to convert this fact into WFF, that means well formed formula. And then next step is we have to convert it into closed form. So resolution only works on close. So we have to this conversion is compulsory. So we will see how we can convert this WFF into closed form. Here we will discuss about converting WFF to closed form. So there are 7 steps are there. First one is eliminate implies, then move not inward, then standardize variables, then columnization, drop all, then that is universal quantifiers, then convert CNF, then split into close. These are the steps we will discuss in detail. So here first is remove all implies. So there is a rule you can see here. If it is P implies Q is equivalent to not P or Q. So that means we can, if we have a P implies Q, we can remove this implies and we can convert it to not P or Q. Then next step is move negation inward. So that means you can see here, if it comes like this, double negation of negation A, that means A. So then negation of A and B, that is De Morgan's law, that will become negation of A or negation of B. Next one, negation of A or B will become negation of A and negation of B. Then we have a quantifier rules, that is for all x, we can call it as all x, negation of all x P of x will become sum x negation of P of x. Then negation of sum x P of x will become all x negation of P of x. Then the third step is standardized variables. That means each quantifier must use a unique variable name to avoid the confusion. So for all x P of x and for all x Q of x. So in both quantifiers are using the same variable, one must change to another variable. So that means we can write like this: for all x P of x or for all y Q of y. So the variable name don't matter, but they must not clash. Next, the fourth step is move all quantifiers in order to the left of each WFF without changing their relative order. So that means bringing all quantifiers to the in front of the formula without changing their order. And this form is called a premix normal form. Here the only quantifiers are moving, the logical meaning does not change. Here we can see for all x p of x or for all y q of y, we can write like this. This q is all y is also moved to here. You can see here for all x, for all y, p of x or q of y. And the next step is remove existential quantifiers, and this process is called as columnization. Here you can see existential quantifiers means this one, sum x. So here this existential quantifiers are eliminated, not dropped. Here you can see that sum x p of x becomes p of c, and this c is called a news column constant. And then for all x sum y q of x comma y, if it is like this, for all x sum y q of x comma y, it is replaced with the for all x q of x comma f of x, and this is called this f of x is called as column function, and this is called as columnization. And this actually this column function that depends on x. Here the purpose is remove the existential quantifier without changing the satisfiability. And next step is drop the universal quantifiers. That is for all x p of x will become p of x. So after columnization, all remaining quantifiers are universal, and since all variables are assumed universal, we can drop universal quantifier, and this actually simplifies the expression. Next, the seventh step is actually apply the associative property of disjunctions. Here you can see P or Q or R will become P or Q or R, and remove the brackets, it will become P or Q or R. And here actually remove the unnecessary brackets using associativity. Then next step is actually convert to CNF, that is resolution means congestion of disjunctions. Here we have to remove all the disjunctions of conditions from the predicates. So here we can see the example P and Q or R, that will become P or R and Q or R. So here this is actually applied repeatedly until there is no disjunction contain a congestion inside it. So this is the most important step. Here we need the resolution needs congestion of disjunction. So here if there is any disjunction contains any congestion, then we have to remove it. So we will do it repeatedly, and then it will become each part of the congestion become one clause. So that is the next step. Create a separate clause for each congestion. You can see here after converting like this, it will become P or R is one clause and Q or R will become the next clause. Next is rename variables in the clause resulting from step 9 to ensure that no two clauses refer to a same variable. So ensure that no two clauses share the same variability. And this avoids the unification confusion during resolution. Unification we will see in detail in the later slides. Now we can see the examples. Here we can see that for all x, then not of Roman x implies Pompeian of x and not of 8x comma Caesar. So first step is we have to eliminate this implies symbol. So how we can eliminate? So we have already we have an equation, that is P implies, one second. So here I can write. So if I have P implies Q, then I can write like this, not P or Q. So here Roman of X is the P and this is implies symbol, and here we have Q is Pompeian of X and not of 8x comma Caesar. So here we can write not P. So that is not Roman of X. Then or you can see here it is or then Q. Q we are writing as such Pompeian of X and 8 of X comma Caesar. Then here we can move this negation inward. You can see here this negation and negation will cancel, so it will be Roman of X, and then this negation, if it moves to inwards, this or will become and negation of Pompeian of X and not of 8x comma Caesar. Then if we are moving this negation inward, then it will become not of Pompeian of X and this not moving inward, then this and will become or. So here you can see or, and this negation and negation will cancel each other, so it will become 8x comma Caesar. So this is the way we can move this negation to the negation inward. Then next is to we can demonstrate the standardization of variable. Here you can see that for all x, for all y, animal of y, x comma y, and some y, louse y comma z. So here we have two variables. Here you can see here we have x is one variable and x is one variable and second variable is y, and again here it is all y, and again we have some y also, so there is a confusion, so we have to give a unique variable name. So it will become for all x, for all y, animal of y, louse x comma y, and this will become some z, louse z comma x. Next, we will see the fourth step example. That is, we have to move all the quantifiers to the left side without changing their relative order. Here you can see this will become for all x, all y, and some z, and some z, and that move to the left side. Then the remaining part we can write as such: animal of y and a louse x comma y, or louse z comma x. So after the first four processing steps of conversion are carried out on original statement S, and the statement is called the Phoenix normal form. So next we can see the step number 5. So we have to do the next step is actually step number 5, columnization, and here we are just we are considering an example. You can see here some y, president of y can be converted into president of S1. So where S1 is the function that somehow produces a value and satisfies president of S1, and here S1 is called a column constant. Another example you can see some y for all x that leads to y comma x. So here the value of y actually satisfies the satisfies the leads depending on a particular value of x. So hence the above statement we can write for all x that this sum y and y that will become f of x. So this will become for all x leads f of x comma x, and this f of x is called a column function. Next step is actually we can drop the universal quantifier. We can remove all this universal quantifiers, and the remaining part we can keep it as such. You can see here not of Roman of x, or not of no x comma y, or 8 y comma z. And next step is convert the formula into conjunction of disjunction. You can see here Roman or 8 x comma Caesar and not loyal to x comma Caesar. This is the one sentence we have, and here we can consider this part is P and this part is Q and this part is R. So it will become P or Q and R. So we know that if the equation is in the form, how we can write this? We can convert this into two flows. That is, we can write like this: P or Q and P or R. So we have already discussed this, and this we can convert it into clause, and this is one clause P or Q, and P or R will be the next clause. Then next we will see the resolution procedure. So we have already seen the resolution process is a iterative process, and each step two clause called parent clause are compared, and there is a resulting new clause is formed, and that is the process of resolution. So we can say that it's a simple iterative inference process. Um, at each step, there is a two clause, that is parent clause, that is selected and are resolved to produce a new clause called a resolvent. And this resolvent actually captures the logical interaction between two parents. Here we can see that if one clause contains a literal L and another clause having a component negation of L, that is not L, then this L and not L, that will cancel. So that means that we can remove it and combine the remaining literal, and the result is called the resolvent. And here we can see that it's given that winter or summer and not winter or cold. So here this complementary literals winter and not winter we can remove here. You can see here. Here we have winter and here we have not winter. So that means we can remove winter and not winter and then combine the remaining literals. So it will become summer or not cold. It can we can combine it as summer or not cold. So here if winter is true, if the winter is true, if the winter is true, so then the cold must be true to satisfy the second clause. So if the winter is false, if the winter is false means the winter is false means then the summer must be true to satisfy the first clause. So in both cases, at least one of summer or cold is true. So the resolvent contains all the literal from the both parent clause except the complementary pair. And if the resulting clause has no literal, it is called an empty clause. Uh, Here you can see that winter, winter or summer, and not winter and summer. So here the apply clause represent them in if when we are solving here when we are solving, then if we are getting an empty clause, that means that the empty clause represent false. This indicates a contradiction. So contradiction means there is a false in the our assumption, and whatever we have to prove, that is actually true. That we will discuss in later in the example. Resolution is an inference rule that derives a new clause by eliminating the complementary literal from two parent clauses actually. And it's deriving the empty clause indicates a contradiction and proves the goal. Next, we will see the algorithm for resolution in detail. The first step is converting the WFF to clause form. That is, convert each sentence in the knowledge base into clause form. And this actually involves removing implications, pushing the negations inward. Then next is the colonization and then converting to congestion of distinction. So each clause is added to the clause. Then the second step is add the fact or query P to be proved to the set of clause. That means to prove a statement P, the resolution uses proof of refutation. That means negate the goal. And then if the goal is P, then we are converting it to not P. And this converted not P, we have to convert it to a clause form. That is apply the same clause form conversion steps. Usually they result in a single clause. Then add the negated goal clause to the existing clauses from the knowledge base. So, for example, you can see here if we have like Tommy, comma cookies. So we are first we will negate the goal. So negation of goal is not like Tommy, comma cookies. then it is converted into closed form. It is already a closed form. There is no conversion is needed. So we can add this to the closed set. Next third step is repeat the following step until the proof succeeds or fails. So the first one is select two clauses. That means choose any two clauses from the current clause set that contains the complementary literals. That is P and not P. So then resolve the clause using unification. That means identify a literal P, P is one clause and not P is another clause, and apply the unification. Unification we will discuss in detail. So that means to make the literal identical and then remove this complementary literals and combining the remaining literals to form the resolvent. So for example, you can see here P of x and or Q of x is one clause and R of x or not P of x is another clause. And here we have two complementary clause. You can see here P of x and negation of P of x. And these two will cancel. So we can remove this complementary literals and we can the remaining literal we can combine. That means Q of x or R of x. So here, if the empty clause is derived, so if the resolvent is empty clause, so that means it is there is a contradiction is found. If not empty clause, then add that resolvent to the clause set and they will continue. So that means the empty clause is derived. That means a contradiction is reached, and therefore we can conclude that the original query is true. So that means succeeds. Next is if there is no clause can be generated, no new clause can be generated. That is empty clause is not obtained. Then the query cannot be proved from the knowledge base. So here the resolution uses proof by a refutation and the unification is required in the first order resolution that we will discuss. Then empty clause represents that empty clause means that whatever assumption we have taken that is false. So there is a contradiction. So that means the goal is the resolution proceeds by repeatedly resolving a pair of clause using unification until either the empty clause is derived, that is proof succeeds, or no new clause can be generated. That means proof fails. We have already discussed this. If the resolvent obtained during the resolution process is an empty clause, then the contradiction has been found. So, for example, if here you can see g of x and not g of x. So, there are two clauses. This complementary literals that g of x and not g of x set. So, it will cancel. That means after removing both, there is no literal remains. So, that means an empty clause. So, the empty clause represents false. So, that means whatever will be our assumption that is false. So, what is our assumption? That is the negation of our goal. So if the result is empty clause, it means our assumption is wrong. So the original clause to be proved has to be true. So if the empty clause represent false means our assumption is false. It indicates that the current set of clause is inconsistent. So since the knowledge base is assumed consistent and the consistency must be due to the negated goal. So our conclusion will be if the resolution result in the empty clause, it means that the assumption is wrong, that is the negated goal is wrong. Therefore, the original goal, that is query is true. So, derivation of the empty clause during resolution indicates a contradiction, proving that the negated goal is false, hence the original query is true. Thank you.